Okay, good morning. This is our ninth session, and in the previous session, we have started a numerical problem, and the numerical problem is related to a simple aircraft air conditioning cycle. Okay, so in this, we have uh, six different points starting from one, and of course whenever we have the ram process, compression process and the turbine process, all these processes are nothing but the actual processes. So each of the process has some amount of isentropic efficiency involved. So that is the reason we are reaching at point 2 days, 3 days and 5 days. In addition to that, whenever we are doing this heat transfer process in the heat exchanger, in this process we also have some amount of pressure drop involved. Okay, so based on the given data, which mainly was the speed at which aircraft was flying, temperature and pressure at the inlet of the aircraft, efficiency of compression, turbine and ramming process, as well as the ratio of pressure across the compression, that was 5, and other two data were effectiveness of heat exchanger was 0.8 and pressure drop in the heat exchanger was 0.1 bar, and P6 and T6, which represents nothing but the cabin pressure and temperature, these were 1.06 bar and 25 degrees Celsius. So these all were the given data, and then using different relations which we can apply for the individual processes, based on that we have calculated the values of temperature and pressures at all the data points. Now what we have in addition to this, after estimation of pressures and temperatures, we have to find the COP as well as the mass flow rate of the working fluid. So mass flow rate of the air which we are actually passing through different components. However, when we have to calculate the mass flow rate, we need to calculate it for how much tons of refrigeration capacity? For 1 ton of refrigeration capacity. Is this point clear? So it means that refrigeration effect is already given in the question, and refrigeration effect is how much? 1 TR, and 1 TR is nothing but equal to 3.51667 kilowatts. Is this point clear? So that is the definition of 1 ton of refrigeration. Now, how this refrigeration effect can be employed for estimation of the mass flow rate? Please tell me. What is refrigeration effect? Refrigeration effect is how much heat is taken by air in the cabin. Okay, so if you see, as per our cycle diagram, the air was entering the cabin at temperature of T5 dash, and it was leaving out of the cabin at a temperature of T6. So it means heating of the cooling air has taken place from 5 dash to 6 point. So this is basically the refrigeration effect. Okay, so this is the inlet and outlet condition of air after taking the heat from the refrigerated space, which is cabin in our case. Is this one clear? So this refrigeration effect I can directly write equal to nothing but mass flow rate of air into Cp of the air into T6 minus T5 dash. Anyone is having any objection about this? All are fine with this? So from here T6, T5 dash we have already calculated. Cp we know 1.005 for air, kilojoule per kg Kelvin. From here if you calculate mass flow rate of air, how much it is? Please tell me if someone has calculated.
541 kg per hour.
Okay, 541 kg per hour. Kg per hour. Calculate in kg per second.
Kg per second.
Divide by 3600.
0.15.
0.15 kg per second. So this is the mass flow rate. Okay. So if I know the mass flow rate of the air, now I can calculate ram work, compression work and turbine work. How much will be ram work? Please tell me. What is the ramming process? 1 to 2. Okay, and actual process is 1 to 2 dash. So mass flow rate of air into Cp into T2 dash minus T1. This will be nothing but my ram work. So tell me, what is the value of this? Please calculate the ram work and let me know how much it is. How much is ram work? 5.83 kilowatt. Okay. Next, what we need to calculate? W compressor. What is the process of compression? 2 dash to 3 is the ideal. Actual process is 2 dash to 3 dash. So mass flow rate of air into Cp into T2 dash minus, sorry, T3 dash minus T2 dash. It will be coming the compressor.
So the SI unit for mass flow rate is per second only.
Kg per second. Okay. So how much it is? Please tell me compressor work. $32.87 kilowatt. Then what is next? Turbine work. Which process is happening in the turbine? Please tell me. 4 to 5 is ideal, 4 to 5 dash is actual. Okay. So m dot air into Cp into T4 minus T5 dash. How much it is? Close to 9.85. Is this one clear? Now, what I need to calculate? I need to calculate W dot net. How much will be W dot net? Please tell me. Compressor work will be a positive work. So, W dot C, which is work done on the system, work done by the turbine is output we are getting. So, that output also we are utilizing. So, minus W dot T. Will I be considering ram work over here or not? I will not consider ram work because ram work is not at all involved in the refrigeration process. It is actually involved in the propulsion process. Okay, so that's why in case if you assume that your engine is on the ground, so probably there also, though because of the converging effect, there can be some ram work, but its amount will be very small. Okay, but ultimately it does not contribute to compression, contribute to refrigeration process, because in refrigeration process only the which process is required, the actual compression process is required, which is happening in the compressor. Okay, so ram work, though it partly help in the compression, but its load comes on the engine only. Okay, so that is the reason ram work I will not include over here. So if I take minus of this, how much I will be getting? 23.0 02 or 03 kilowatt. Okay, now you know how much is the W net. You know already the refrigeration effect. So what will be COP? Refrigeration effect divided by W net. Refrigeration effect is 1 ton of refrigeration, 3.51667 divided by 23.03. So how much is COP? 0.1527 is the COP of the system. Is this point clear? So you can see that air refrigeration system is under these conditions, it is having very less. Okay. Then after this, what else is asked in the question? I think 2 more parts are left. Volume flow rate at the exit of compressor and exit of turbine. Okay, so we are considering that we are using air standard assumptions. So if we are considering air standard assumption, it means we are following the ideal gas equation. So as per ideal gas equation, PV is equal to MRT. Okay, and if I have to write this ideal gas equation in rate form, then how I can write? PV dot, where V dot represents the volumetric flow rate. Then in the right hand side, in place of mass, I have to write mass flow rate, m dot into RT. Okay, so I can simply apply this equation. Now it is asked in the question that calculate volumetric flow rate V dot at the exit of turbine and exit of compressor. What is the point at the exit of turbine? 5 dash. So P5 dash V dot at turbine outlet will be becoming equal to m dot air, because we are not bypassing any air. Whatever the air is starting at point 1, same air is actually passing through the turbine and same is going through the cabin and compressor. Everywhere same amount of air is actually flowing. Okay, is this one clear? So that's why m dot air into R will be a constant and T5 dash. This we will be writing, and from here if I calculate V dot TO, it comes out how much? 403.811 meter cube per hour, if I calculate in meter cube per hour. Is this one clear? And similarly, at the exit of compressor, point is 3 dash. So you can write P3 dash V compressor outlet, V dot compressor outlet equal to m dot air into R into T3 dash. From here you can calculate V dot CO. All are clear with this? Please tell me. Anyone is having any doubt? Please quickly tell me. Anyone is having any doubt? So you have come to know how to solve the numerical problems. Okay, so if you know the processes, their thermodynamics behavior, you can actually easily step by step solve the numerical problems of all the air refrigeration cycles. Okay, so maybe I'll try to give you small assignment based on this unit, aircraft air conditioning, and the previous unit, which was the introductory unit. Okay, so do that assignment and try to do the assignment by your own. Okay, because ultimately that will be helping you in the exams. Okay, because in exam also you will be finding numerical problems. Okay, so with this unit 2 is over, do you have any questions on unit 2? Please tell me. Is there any question? After this, as per your syllabus, we will be following the unit 3, and unit 3 is nothing but our vapor compression refrigeration cycle. Refrigeration, instead of cycle, I will be writing cycles, because different types of vapor compression refrigeration cycles we will try to analyze this. Okay, so already I have introduced you to the very fundamental vapor compression refrigeration cycle. Can you tell me what is that? Already I have introduced you. Vapor compression refrigeration cycle, the fundamental one, when I initially introduced you to the refrigeration system. Rankine is a power cycle. Which vapor compression cycle I have introduced you earlier, which is using vapor as a liquid and vapor as a medium. Do you people see notes after the class? Reverse Carnot cycle. Okay, what was there in the reverse Carnot cycle? Again, I need to repeat, I think. What was there in the reverse Carnot cycle? What are the four processes involved? Okay, then isentropic. After heat addition sequence is compression. Then after that please tell me how we were achieving this. All the processes. If we have to now, please consider this point very carefully. Now we need not to use air. What we use? We will be using a medium which is operating in between the liquid vapor dome. Okay. So how I can achieve this cycle? I'll be using some heat exchanger which is called as evaporator. Then I'll be having compressor. Then after that I'll be having another heat exchanger which is called, then I'll be having turbine. Okay. Now first you tell me one thing. Why I am calling these two as evaporator and condenser, whereas in the air refrigeration cycle I was just calling these as heat exchangers. Because in case of air refrigeration cycle, there was no phase change of the working fluid. Working fluid was staying in the same phase. Whereas in this case, particularly the bottom heat exchanger, because here also it is gaining heat from the refrigerated space, and here it is giving heat to the ambient. Okay, so from refrigerated space, whenever it is taking heat, my working fluid is changing its phase from liquid to vapor. This process is nothing but evaporation process, okay, or phase change process where liquid is changing into vapor. So now the heat exchanger in which liquid changes phase from liquid state to vapor state is called either evaporator or boiler. Is this point clear? Then we have the another type of heat exchanger in which working substance changes phase from vapor to liquid, that is called as condenser, because the process of conversion of vapor to liquid is nothing but condensation process. All are agreeing to this point? Okay. So this is my basic cycle. I think I need not to explain it again in very detail because already I have given you the many details about this cycle. Okay, if I am talking about the reverse Carnot cycle, then it is nothing but a totally reversible cycle. So if it's a totally reversible cycle, the refrigerated space, if it is having TE temperature, the working fluid also will be having TE temperature in the evaporator. Here if this is TC, here also temperature has to be TC, because then only process will be totally reversible. All are clear with this point? Then in the compressor I will be supplying WC amount of work, and in the turbine I will be getting output WT amount of work, and net work input to the system will be WC minus WT. All are clear with this point? Now after this, if I have to represent this on TS diagram, how I can represent it? Remember, in case of air refrigeration system, we were operating purely in the gaseous phase, so we were drawing our diagram significantly away from the liquid vapor dome. But now, whenever my working fluid is moving within this system, it is continuously changing phase from liquid to vapor and vapor to liquid. So it has to be operated in between the liquid vapor dome. Okay. So first I will be drawing the liquid vapor dome. Now within the liquid vapor dome, these are my say two temperature limits, TE and TC. I have to now draw the cycle in such a way so that I am having isothermal heat addition and heat rejection and isentropic expansion and compression. So any process along these lines will be isothermal and any process parallel to vertical will be isentropic. So this is my Rankine cycle. Showing all the, sorry, this is my reverse Carnot cycle showing all the four processes. Is this one clear? This already I have discussed. Okay. Then after this, what we will be having? What were the limitations? What were the practical issues? First is, practically we do not have any device which can compress mixture of liquid and vapor. Okay. So I cannot start compression process at point 1. I must add heat up to the point TE, because up to TE also process will remain isothermal, and from this point then I can achieve the compression process. Is this point clear? So if instead of using this point, if I go up to this point, say 1 dash, and then if I do the compression process, in that case what will be happening? If I have to follow the Carnot cycle, I need to do the heat addition, heat rejection process also in an isothermal fashion. Okay, so to do this process in isothermal fashion, the heat rejection process should follow this line. Is this point clear? So if it has to follow this line, I have to stop here compression at some point 2 days. Okay, but you will be also coming to know that if I have to draw constant pressure line on TS diagram, how it looks? Like this. This is one constant pressure line, say, representing condenser pressure. This will be another constant pressure line which is representing evaporator pressure. Okay. Likewise, I will be having another constant pressure line which will be passing through point 2 dash. Okay. Now the constant pressure line which is passing through point 2 dash, it is in between PC and PE. So it means corresponding to point 2 dash, I will be having some intermediate pressure PI, which is greater than PE but less than PC. Okay, so it means that from process 1 dash to 2 dash, I have to actually do this isentropic compression, but this isentropic compression I have to do only from pressure PE to pressure PI, which is less than pressure PC. Is this point clear? Now, if you see from 2 dash to 2, what is process 2 dash to 2? It is isothermal heat rejection process. It means I have to reject heat and parallelly the temperature should remain same. And third condition is also there. What is the third condition? When I am moving from point 2 dash to point 2, the pressure is changing from PI pressure to PC pressure. Where PC pressure is greater in comparison to PI. So it means that I have to use isothermal compressor. Is this one clear? So to achieve process 2 dash to 2, what I need to do? I need to employ isothermal compressor. Yes, please. Yes, there we will be going for the actual cycle, but right now if you are saying that instead of this I go up to PC and then I start cooling, then will your heat rejection process will remain isothermal? Yes, until it is saturated vapor, it will not be isothermal. So at present, what we are trying to do? We are trying to move the cycle in such a way so that I can exactly mimic the Carnot cycle. Okay, so for exactly mimicking the Carnot cycle, I am trying to do 2 dash to 2 process in an isothermal compressor. Is this one clear? Of course, whatever you are saying, that is correct. Practically, we have to do that only. That is why we will be moving again from this type of Carnot version to the towards the actual cycle. Is this one clear? So again, I have issue. What is the issue in this cycle? Please tell me. I can run an isentropic compressor and one isothermal compressor. What is the issue? Can I not run two compressors? It's very easy for me to run two compressors. What is the issue with this? Already I discussed the issue when I explained the gas Carnot cycles. Because in gas Carnot cycle also we were having two isothermal compressors, two isentropic, one isothermal compressor, one isentropic compressor, and one isothermal turbine, one isentropic turbine. So what was the limitation over there? Sorry? What is the issue? That is the other point. Say isothermal heat addition and isothermal heat rejection will generally takes either infinite large surface or infinite amount of time. Okay, so it means these two are not feasible. That is one limitation. Presently, I am asking about the compression process. Can I not follow 1 dash to 2 dash and 2 dash to 2 so that I can achieve isothermal heat rejection? Here, what is the limitation? You people are forgetting very fast. So I told you that isentropic compression means I have to operate in reversible adiabatic manner. It means whenever the working fluid is moving in the compressor, it should not exchange heat with the surroundings. So if fluid parcel is entering inlet of compressor, that should immediately go to outlet so that it does not get finite amount of time for heat exchange with the surrounding. So process inside the isentropic compressor has to be very fast, whereas in isothermal compressor, if you do compression by a small amount, then you should also reject the equivalent amount of heat so that your temperature should not increase. Because of the compression process, what happens? If you have a piston cylinder system, all of a sudden you press the piston, what happens? Temperature increases. But if you slowly move the piston, then temperature of air increases? It doesn't increase because of the compression process, whatever slight increase in the temperature is there, you have allowed finite amount of time for gas to dissipate that heat to the surrounding. So you are doing compression in a quasi-static fashion. So here isothermal compressor should operate at the very low speed. Okay. So in a complete closed loop cycle, one device wants that working fluid should move fast, other device wants working fluid should move slow. Can there be continuity of flow? No, not possible. Okay. And of course, other two limitations you have clearly indicated. These are nothing but the isothermal heat addition and isothermal heat rejection are actually challenging processes because these will be either requiring large amount of time, which will make the whole cycle process slow, or again contradicting with the isentropic compression, or you require infinitely large amount of heat exchanger to produce some finite amount of heat transfer. Is this point clear? So these were the limitations which we discussed. Again, I have already discussed. I am again repeating today. Up to this point, it is just the repeat of the previous one. Okay. Now, COP again I have derived for the reverse Carnot cycle. I am not going to derive it again. But COP of reverse Carnot cycle will be simply TE upon TC minus TE. Is this point clear? So now it means that these are some of the limitations with the help of which I cannot operate the reverse Carnot cycle practically. However, still we use this reverse Carnot cycle as a benchmark for comparing the performance of the actual cycles against a reference case, which gives us idea that how efficient is our actual system with reference to the Carnot cycle. Okay. So what I could do in order to make this process reversible, what I can do? Sorry, not reversible, practical. What I can do? I will now take a cycle which is called as triple S thermodynamic cycle. Standard single stage vapor compression cycle. So we will try to move now towards the standard single stage vapor compression cycle. Okay, and later on you will be finding that this cycle is nothing but the reverse of the Rankine cycle. So it is also called as reverse Rankine cycle. Okay, so another name we can propose to this cycle is nothing but reverse Rankine cycle. And moreover, whatever the cycles which we are studying under the class of vapor compression systems, these typically in general are also called as Evans-Parkinson's cycles. Why? Because if you recall, in the history lecture I told you that whenever the initially ethyl ether was tested for refrigeration, then the first hand compression operated cycle was proposed by Parkinson's, and before that its idea to operate in encyclic fashion was proposed by Evans. So that's why all the vapor compression cycles comes under the categories or in general are called as Evans-Parkinson's cycles, particularly involving the single stage compression. Okay, is this one here? Now in the previous cycle we found that this 2-2 process is actually creating the trouble. Okay, so my problem will be solved if I make over here two assumptions. First assumption is, in place of assuming the totally reversible processes, let me assume that all the processes are only internally reversible. If processes are internally reversible, then the processes are possible. Why? Because internally reversible means within the working fluid there should not be any temperature gradient. Okay, and how that is possible? Because I am operating in the saturated liquid vapor dome. So in the saturated liquid vapor dome, when I will be adding the heat, despite temperature change, phase will start converting from liquid phase to vapor phase at the same temperature till the saturated vapor state is achieved. Similarly, in the heat rejection process, if I keep on removing the heat, then vapor will start converting into the liquid phase. Okay, so first relaxation which I need to do in my assumptions, first relaxation is I will be considering now that all the processes are nothing but internally reversible instead of the totally reversible processes. Okay, what about the other thing? Other thing is, the major challenge is with this new red colored cycle, now I have a device available at point 1 dash, a compressor which can compress the pure vapor. Okay, but the issue is I cannot simultaneously operate isentropic compressor and isothermal compressor. So isothermal compressor is actually now the issue. So what I can do, I can remove this isothermal compression process. I will do compression up to point up to the condenser pressure PC. Okay, and then I will give another relaxation that heat rejection process is isobaric instead of isothermal, because part of the heat rejection process will be actually taking place in superheated zone, where the upon removing the heat, the temperature of the working fluid will decrease. So this will not maintain the isothermal condition, but it will be a isobaric condition. All are clear with this point? So what relaxation, second relaxation I have given, that heat rejection process is isobaric. All are clear with this point? What else? If you talk about heat addition, it will be both isobaric and isothermal, because in heat addition again I am operating within the dome only, so it will be both isobaric as well as isothermal. Okay. Okay, so with these changes, if I now draw the cycle, what I get? On this TS diagram, I have drawn the two lines. One is at PC pressure and other is at PE pressure. My compression process should start from which point? This point, saturated vapor state. Okay. Isentropic compression will take place up to point 2. Then from here I will start removing the heat. So when I remove heat, initially the temperature will keep on decreasing along the constant pressure line. It will come up to saturated vapor state. Then at saturated vapor, phase will change and I will be reaching to point 3. Then 3 to 4 I will be doing the expansion in the turbine. And 4 to 1 again I will be going in the. So here in process 4 to 1 I am adding QE amount of heat. Here I am removing QC amount of heat. Here I am adding WC amount of work, and here I am getting WT amount of work output. So this cycle is at present is a practical cycle. And if you recall the Rankine cycle, okay, so cycle is same, only the direction is changed. Direction is reversed. Okay. So this is the reverse Rankine cycle. Now, if we have to do thermodynamic analysis of this cycle, how we can do? Again, we have to start with the steady flow energy equation, because all the individual devices are nothing but steady flow devices. Okay. So process 1 to 2 is what? Isentropic compression. Okay, and it's a steady flow process. So for a steady flow process, in general, I can write, I am writing on per unit mass basis, heat input plus incoming enthalpy plus Vi square by 2 plus GZI has to be equal to work done by the device plus outgoing enthalpy plus VE square by 2 plus GZE. If E represents exit, I represents inlet. Is this one clear? This is for a single inlet, single outlet steady flow device. Now 1 to 2 process is isentropic. It means Q is isentropic, means it's reversible adiabatic. So Q is 0. Incoming enthalpy is H1. If I make assumption that inlet pipe of the evaporator and inlet pipe of the compressor and outlet pipe of the compressor have almost same size, or their size are changed in proportion so that their velocity at inlet and outlet are same, then changes in potential and kinetic energy can be neglected. Normally their magnitude is very small in comparison to the change in enthalpy, so these are mostly neglected. Okay, so that's why I can simply write this term equal to 0. Then WC amount of work is done. Compressor, it is done on the compressor. So if it is done on the compressor, I must place a negative sign, minus WC, and plus H2. So from here my WC will be coming equal to nothing but H2 minus H2. Is this point clear? Now you tell me, can I write this H2 minus H1 equal to Cp into T2 minus T1? Can I write it? H2 minus H1, can I write Cp into T2 minus T1? Right now, I am operating a vapor medium, and vapor medium cannot be approximated as an ideal gas. Okay, so delta X equal to Cp into T2 minus T1, it can easily be applied for ideal gas. Whenever my ideal gas assumption, air standard assumptions are not applicable, then I cannot write this to Cp into H2 minus H1. Of course, both point 1 and point 2 are in the superheated state. So it means your argument is both are in the gaseous state. Okay. So if you see in thermodynamics textbooks or even anywhere, if you see normally the ideal gas assumptions, what are the ideal gas assumptions? Any gas at very low pressures and high temperatures behaves as ideal gas. But whenever we go the reverse way, low temperature and high pressure, then it does not behave as an ideal gas. Okay. So what you can do, you can refer to any of the standard textbooks of thermodynamics, for example, Sontag and Sengel. There you will be finding that they have given a plot of TS diagram or any other property diagram where it is shown that in which zone of the superheated regime your assumption of ideal gas is applicable with good accuracy, whereas when you are closer to the saturated vapor state, there these assumptions are not valid. Okay, is this point clear? So that's why ideal gas assumption will not be applicable for this type of working fluid. So that's why you cannot write delta H equal to Cp into T2 minus T1 directly over here, because it is not following air standard assumption. So what we need to do? We need to follow the property tables or property charts. Have you used steam tables? So the way you used steam tables, depending upon the working fluid, if my working fluid is water in the refrigeration cycle, then I will be referring to steam table. If my working fluid is any other refrigerant, then I have to actually refer to the property tables or charts of that particular refrigerant. Is this point clear? So please don't write H2 minus H1 equal to Cp into T2 minus T1. Okay, and this will be in kilojoule per kg, because I am writing it on per unit mass flow rate basis. If I write capital WC, which will be equal to mass flow rate of the working fluid into small wc, that will be becoming m dot into H2 minus H1, and kilojoule per kg into kg per second, kg will cancel, kilojoule per second will become kilowatt. Is this one clear? Likewise, if I go for process 2 to 3, please tell me what will happen. In 2 to 3 process, I am removing QC amount of heat from the working fluid. So QC will be negative with minus sign, because heat is being rejected. Heat rejected is considered negative. Plus H2 is incoming enthalpy. Okay, equal to, there is no work done, and H3. From here QC will become equal to Please tell me. H2 minus H3 kilojoule per. Go to process number 3 to 4. There is no heat. H3 is incoming enthalpy. Work is done by the turbine, which is considered positive. Wt plus H4. From here, Wt will be becoming equal to H3 minus H4. Okay? And then come to process number 4 to 1. What I will be getting over here? Heat is added to the working fluid. So QE will be positive. There is no work. H1 minus H4. All are agreed to this point. If you have to calculate COP, what will be COP? Please tell me. H1 minus H4 divided by net work done. What will be net work done? H2 minus H1 is compressor work minus H3 minus H4 is turbine work. So that will be my COP of the cycle. All are agreeing to this point? Now, in your home refrigerator, you have heat exchanger, you have compressor, you have condenser. But do you use a turbine? Have you seen turbine in your AC or in your domestic refrigerator fridge? Anyone has seen turbine there? Have you seen compressor? Okay. Have you seen heat exchangers, evaporator and condenser? You have seen. And then some additional fans also we see in AC, but in fridge you don't see any fan. Okay. Is this one clear? Now, why turbine is not used in AC or fridge? That is first question. Second question is, what is the replacement of turbine in the domestic refrigerators? There should be some component which we are using, which is a replacement to the. Okay, first point is cost. Second point, work output is good, because if compressor is taking some input, turbine is giving output, so net work input, net energy supplied to AC will decrease. It is not that much. You sometime in your home use energy meter for your fridge and AC. In comparison to no, that is something else. There the things are different. Pressure ratios and amount of air handled are different. Please tell me, what is the equipment or device used in place of turbine in AC? Expansion valve, generally we say. So in the older fridge or machines, a small capillary tube were used as expansion device. Nowadays we are having automatic expansion device, solenoid controlled expansion device, different type of expansion device. So first one question is answered that there will be some device which is called as expansion device. Why not turbine? Why expansion device? No, it has to handle small amounts, so it can be small. Size big is required for air, because in case of air you have to handle large volume of the. Okay, so let me give you one idea. Already I have explained you, that's why I am asking it actually. because one time I have already explained you this thing. Why turbine is not used. Okay, you tell me, turbine is nothing but a steady flow device. So here we will be having open work. What will be open work? Work done in an open system, shaft work, minus integral of VdP, where V, what is V? Specific volume. In the turbine, what I am expanding over here? At point 3, substance is in which state? Liquid, saturated liquid state. Saturated liquid has very high amount of density and very low amount of specific volume. Specific volume is 1 by density. So liquid has almost, if you talk about water and its water vapor, then almost 1000 times higher density in comparison to vapor. Okay, so it means that, tell me, specific volume which of the working fluid which is entering the turbine, it is very small. Because of this, the work done by the turbine will be very small. Okay, so whatever the work output out of the turbine you will be getting, that is very small. And generally, the fabrication process of turbine is very intricate. So because of this, the cost of the turbine will be very high. Even a small turbine of few kilowatts may cost 2 lakhs or 3 lakhs. So if you have a big component, okay, installed in that one, so your AC cost will be overall fridges of say 20,000, then it will be becoming 1,20,000 or 1,70,000. And instead of that, whatever the work output you are getting out of turbine, that is very small. So that's why we do not use turbine in the practical devices, and in practical devices in place of turbine we use some device which is called as expansion device. Okay, and because ultimately what is our aim? Our aim is to decrease the pressure from point 3 to point 4. So we will be decreasing the pressure in expansion device, and the process which takes place in the expansion device is actually throttling process. Is this one clear? Do you know about throttling process? All of you have heard this name, throttling process. And then what I will be doing in this cycle, this turbine I will be removing, and I will be passing the working fluid through some device which is called as expansion device. Now you have to understand one important point. In the expansion device, the process is not isentropic, and this is a irreversible process. So in expansion device, because of the irreversibility, there will be generation of some entropy. So because of this, the point 3 now will not follow constant entropy line, but I will be going to some point 4 dash, and this process, generally 3 to 4 dash process, throttling process, is represented by a dashed line. Why dashed line? Because it is not a reversible process. Okay, so all of you please read about throttling process from your thermodynamics textbook when you are coming in the next class. Okay, so in the next class I will discuss this practical cycle in more details.